Nuclear fusion. It powers the sun, allowing it to supply energy to the entire solar system. Fusion entails combining lighter atoms to form heavier, more stable ones, releasing vast amounts of energy in the process. To understand fusion, we first need to appreciate the nature of the atomic nucleus. A nucleus consists of protons and neutrons. Protons are positively charged, while neutrons have no net charge. Atoms of the same element all have the same number of protons, but may vary in neutron number. These variations are called isotopes. The key takeaway here is that the nucleus consists of positively charged protons packed close to each other. Since charges of the same polarity repel each other, this should be impossible. So how do atomic nuclei exist, despite this fact? The only thing that allows the nucleus to exist is a powerful force called the strong nuclear force. This force acts on protons and neutrons over a short distance, and in that regime, it's stronger than the electrostatic force that wants to push the protons away from each other, thus keeping the nucleus intact. Now let's understand how fusion works with an example. Deuterium and tritium can fuse to form helium. Deuterium is hydrogen 2 and tritium is hydrogen 3. For the nuclei to fuse, they have to come together with enough energy to overcome the repulsive electrostatic forces between them, since they are both positively charged. This energy has to be in the form of the nuclei's kinetic energy. Thus, the reactants must be at a very high temperature for fusion to occur. The temperature has to be in the order of hundreds of millions of kelvins in nuclear reactors. This is roughly 6 times hotter than the sun's core. At such temperatures, electrons will have been ripped away from atomic nuclei, creating a state of matter known as plasma. These nuclei are now moving so fast that they cannot avoid colliding with each other anymore. Once they smash into each other, they are now close enough for the strong nuclear force to overcome the repulsion, causing them to fuse and form a new element. Just like in nuclear fission, there is a decrease in mass known as a mass defect. This is because during fusion, some mass is directly converted into energy, the amount of which can be easily calculated using Einstein's mass-energy relation. Attaining nuclear fusion on Earth is a complex and challenging task that requires achieving the extreme conditions necessary for fusion reactions to occur. The most common ways to attain nuclear fusion are inertial confinement and magnetic confinement. With inertial confinement, tiny pellets of deuterium and tritium are rapidly compressed and heated using high-energy lasers. The intense pressure and heat cause the nuclei to fuse. Magnetic confinement uses powerful magnetic fields to confine a hot plasma of hydrogen isotopes, preventing the plasma from coming into contact with the reactor walls. It is very difficult to contain this hot, fast-moving plasma for extended periods. Once the plasma escapes the magnetic confinement and touches the reactor wall, the walls melt and the reaction stops. The Sun, on the other hand, is able to achieve sustainable fusion because its immense gravitational field confines the plasma inside its core. That's it for how nuclear fusion works.